will discuss about my last paper, which has been published very recently. And I'm going to talk about a relic galaxy that lacks dark matter. Now, since I have seen that there's people from a huge variety of backgrounds here, I should first explain what a relic galaxy is. So a relic galaxy is a very special kind of early type galaxies. So galaxies are in general divided between early type galaxies, that is galaxies that have a huge bulge or only a bulge and have no disk, have little star formation, they have all stellar populations, and late type galaxies, which are the nice disk galaxies that have bars and star formation and so on. So a relic galaxy is a very special kind of early type galaxy. Now, most of early type galaxies undergo two-phase formation history. So at the beginning of their lives, early type galaxies form a very compact core through the accretion of small protogalactic fragments or through cold flows. So during the first giga-year, you are having a very small compact thing being formed that is about 1 kiloparsec in radius, and is undergoing a very intense star formation. Then after a giga-year, so let's say at redshift 2 or 3, this thing gets quenched, and this very compact core accretes an envelope of galaxies that are around. So small galaxies that are around the very compact core that form at the very beginning are accreted by the compact core, and those little things that were floating around the compact core are getting their stars stripped, and these stars end into an envelope. So a regular early type galaxy, a normal early type galaxy, say an elliptical galaxy, is formed by a very compact core that was formed in situ at redshift 2 or 3, and then it has an envelope, a diffuse envelope that makes it much more extended. So with an effective radius of several kiloparsecs, say 5-6 kiloparsecs, of stars that have been accreted. So these stars can be very old, but they have been accreted after the formation of this core. Now, relic galaxies are galaxies that have somehow avoided the second phase of the formation of these early type galaxies. So those relic galaxies form the compact core and then somehow avoided to accrete the envelope. Now, these galaxies are interesting because those galaxies are untouched remains of what an early type galaxy looked like at redshift 2 or 3. All the other galaxies, all the galaxies that are not relics, have accreted stuff. So you have a mix of material that has formed in situ and material that has been accreted. So you don't have a clear view of how an early type galaxy look like if you're looking at a regular early type galaxy. But if you're looking at a relic galaxy, the only evolution that the galaxy has undergone since it formed is the passive evolution of the stellar populations. So this opens a window to see how galaxies look like at redshift 2 or 3. Now, the problem with relic galaxies is that they're extremely rare. There's only 3 of them within the local volume, where the local volume is a sphere of 100 megaparsecs in radius around us. So I hope that I have convinced you that relic galaxies are very interesting to objects, since, as I said, they open a window to see how galaxies look like in the very early universe. So if we have one, we should observe it with everything that we have to try to study its properties. So that's what we did with this thing here, NGC 1277, which is the first relic galaxy that was identified as such already 10 years ago. And how do we know that it's a relic galaxy? Well, we know it because if you look at the surface density profile, here we have the surface density as a function of the radius, we find out that this thing is extremely compact. Here we have the effective radius of this relic galaxy, which is about 1 kiloparsec, And here you have, with the orange line, the effective radius of your regular ETG, which is about 5 kiloparsecs. So there's a factor 5 in effective radius between this thing, NGC 1277, and your regular early type galaxy, which means that you have a factor 100 in density, in stellar density for the relic galaxy. This relic galaxy is a very massive galaxy, assuming a regular IMF, well, it's 10 to the 11 solar masses in stellar mass. And also, we know that it formed at once, that it doesn't have accreted stars because it has basically a single stellar population. All the stars have the same age, they basically all have the same metallicity, and they all have the same IMF, no matter what radius of the body of the galaxy you're looking at. So this is the best, cleanest candidate for a relic galaxy that we have in the local universe. So again, this is what motivated us to observe this galaxy in detail. So here we have a nice SDSS image of the galaxy. So the galaxy is here. It is in a dense cluster. It's in the Perseus cluster, some 70 megaparsecs away. So it's surrounded by other galaxies. And we took the deepest data so far with integral field spectroscopy of this galaxy using the CGMS integral field spectrograph at the McDonnell Observatory in Texas. So here we have a plot showing the fibers of the spectrograph and the signal in each one of the fibers of the spectrograph, and here the signal to noise. And here we have NGC 1277, which is our relic galaxy, a galaxy that has remained untouched since it formed at redshift 2 or 3. And here at its side, we have 1278, which is a galaxy with the same stellar mass, but it's a regular early type galaxy. It's a galaxy that has undergone the whole evolution history that early type galaxies usually have. This means that with the same instrumental setup, same exposure time, same observational conditions, we can study a galaxy that is very special, a relic galaxy, and a regular galaxy. In that way, if we find anything odd in this galaxy, and this galaxy is normal, we cannot attribute it that we have to different observational procedures or whatever, because it's exactly the same data set. So the data are uniform, and we can compare the properties of the two galaxies. So just to show you that we are doing better than previous studies of this galaxy had already been observed with adaptive optics by this gentleman here, Uldirim, and this was the kinematic maps of the galaxy that he was obtaining. So here's the velocity map, here's the velocity dispersion map. This is our velocity map, and this is our velocity dispersion map. So you see that it extends further out. This will come critical for the kinematic analysis because, as we know, dark matter dominates in the outskirts of galaxies. So if we want to characterize the dark matter halo of this thing, the further out we go, the better it is. And this applies to all galaxies, and especially for massive galaxies, which tend to be baryon dominated often in the center. Also, because the angular resolution that we are having is not that great, we could not characterize the mass of the black hole in the center. So we complemented our coarse resolution data with adaptive optics assisted data from this paper in order to characterize the mass of the central black hole of the galaxy. So just to show you how different a relic galaxy to your left and a regular early type galaxy to your right are, here we have the rotation curve in black of the relic galaxy. So this thing is a fast rotator. It's more a lenticular galaxy than an elliptical galaxy, still an early type, and has a rotation velocity of over 200 kilometers per second. On the other hand, the regular early type galaxy has a very small amplitude in the rotation curve. You might say we are looking at it face on, but it also is also very different when you look at the velocity dispersion. NGC 1277 has a very peaked velocity dispersion curve, and NGC 1278, because it's much less compact than NGC 1277, it also has a smaller peak in the velocity dispersion in the center. Also look at the horizontal extent of the data. The axis is the same. We see that 1278 is much more extended than NGC 1277. So in order to deduce the amount of dark matter that this thing has, we did a dynamical modeling using genes and isotropic modeling with the code JAM by capillary. So basically what we are doing here is creating models, mass models of the galaxy, obtaining kinematic maps from these mass models that we have generated artificially, and fitting those kinematic maps to the observations. Now, the kinematic maps, well, the mass models include two components. One, which is the baryons, which we sort of know because we know where the stars are. We don't know exactly what the IMF of the stars are, so we have to scale the component of the IMF of the stars up and down a little bit in order to account for different slopes of the IMF. We introduce this as a free parameter in our fit. And the other component is the dark matter halo, which we assume to be a Navarro-Franken white, but we have also tested an ANASTO, and Paolo, don't kill me, we also tested a generalized Navarro-Franken white. But I mean, the results are the same no matter what we try. Here we are having the fit for NGC 1277. So the parameters that were fitted were this thing, which is related to the inclination of the galaxy, this thing, which is related to the shape of the velocity ellipsoid, and the two important ones here, this thing that tells us about the IMF, and this thing here, which is the fraction of dark matter within 6 kiloparsecs of the center. So here, it tells us basically the mass to light ratio. One would be a mass to light ratio corresponding to a salpeter IMF. So this thing is more bottom heavy than salpeter. It has here 1.3, which would correspond to a mass to light ratio of around 7 in R. And here we are having the dark matter mass fraction within 6 kiloparsecs. Why 6 kiloparsecs? Because this is our radial coverage. And the posterior distribution peaks at 0. Okay, so we have a strong preference for a 0 dark matter fraction within 6 kiloparsecs. Now, of course, this has some error bars. At 2 sigma, we are allowed to have 5% dark matter fraction within the radius we are covering. Now, if we do the same, we do the same thing with the regular early type galaxy. Here we obtain a lower mass to light fraction. It's much closer to a salpeter one. Here we also fitted the mass of the black hole, but this is of secondary importance. But here we find the dark matter fraction for this galaxy is about 15%. So with the same data set, with the same procedure, for the relic galaxy, we find dark matter fraction that is small, compatible with 0, not necessarily 0 because we have some error bars. And here we are finding dark matter fraction within 6 kiloparsec of 14%. Now, how unexpected is that? Well, we should compare our results with what comes out from cosmological simulations. So here we are having perhaps the most difficult plot of the talk. Here we are having cumulative mass within a given radius, within a given 3D radius, shall I say, as a function of the radius. So the purple line here corresponds to the cumulative baryonic mass within a given radius as a function of the radius for NGC 1277. And here, down below here, we don't see it, we would have the cumulative dark matter mass. Now, this gray region here is the 2 sigma profile. This upper line here is the maximum dark matter profile allowed at 2 sigma. What are the cosmological simulations telling us? That for a galaxy with this stellar mass, we should expect this line here. And the uncertainty, the 2 sigma uncertainty due to cosmic baryons and things like that, would be this red region here. Okay, so I wouldn't say that they are clearly incompatible, but they are not spot on top of each other. On the other hand, if you go to NGC 1278, the regular galaxy, same thing here. You got the baryonic component, and here the black line indicates the cumulative mass within a given radius for the dark matter. And in blue, the blue line gives you what is predicted from cosmological simulations for a galaxy with its stellar mass. The red one gives you for a galaxy with that stellar mass at redshift 3. So we see that it's quite spot on that our dark matter profile, fitted dark matter profile, is clearly within the expected range for the simulations. There's no fine tuning here. It just happened to be that way, that it's spot on it. That's a coincidence. But perhaps the most important plot is this one. So here is, well, we're observing NGC 1277 out to 6 kiloparsecs. So for a galaxy with the mass of NGC 1277, sorry, I should rewind a little bit. So 6 kiloparsecs in the case of NGC 1277 corresponds to 5 effective radii. So 5 effective radii. So for a galaxy with the stellar mass of NGC 1277, how much dark matter we expect to have within 5 effective radii? And the answer is about 50%. And we are finding 5% or less. Now you might say, you're cheating with this plot because this galaxy is extremely compact. So maybe you shouldn't measure the radii in effective radii. Maybe you should take the physical size. And perhaps what you should do is to check how much dark matter you are expecting within 6 kiloparsecs. And we do the trick. And here we have the predictions from cosmological models. Here we have 1277, and here we have 1278. So 1278, the regular ETG, falls spot on in the expectation. 1277 is below the expectation, even when accounting with 2 sigma error bars for the expectations and for 1277. So there's a slight tension, I would say, if you take this plot between the expectation from lambda CDM and 1277. So 1277 is a very exceptional galaxy. It's a galaxy in 1,000 or in 10,000. So, well, let's say that it's compatible with being a 3 or 3.5 sigma outlier. But if the relevant plot were that one, it would be a problem for the cosmological model. So since we don't know which plot is the relevant one, I will abstain from saying that this poses a challenge to lambda CDM. Now, we might wonder, what are the implications of the fact that NGC 1277 has no dark matter? And if it has no dark matter, indeed it has no dark matter, and we have not messed up with our modeling, we can explain naturally the fact that NGC 1277 is a relic galaxy. Because if we have no dark matter, we don't have dynamical friction. And if we are not having dynamical friction, we are not accreting things that come nearby. And if we are not accreting things that come nearby, we are not creating an envelope. So that the fact before our dynamical study, it was an enigma why this galaxy is a relic galaxy, why it has never accreted an envelope. Now the enigma is why this galaxy doesn't have dark matter. It's not anymore why it's a relic galaxy. And now comes the hand-wavy part of the talk, because I have no idea why this thing has no dark matter. Unless we have messed up with our modeling. So I will do some hand-wavy thingies, and simulators will have to check whether my hand-wavy thing is absolutely wrong or most likely it is. So we are having 2 possibilities that I came up looking at the literature. One is that this thing is in a cluster. So perhaps as it entered the cluster, some of its dark matter was stripped. We have some evidence of that happening up to a certain point, not up to the point that we are observing for 1277, but up to a certain point in some papers that are checking the TNG50 simulations. So here in blue, we are having the stellar mass of the galaxy as a function of the look-back time. And here we are having in gray the dark matter mass as a function of look-back time. And we see that as it enters in the cluster, the dark matter gets stripped. Now, it's very hard to understand how the dark matter would get stripped without touching the core of the galaxy, okay? It is possible to do it if the dark matter is in very elliptical orbits. It's easier to strip control L. It's easier to strip stuff that is in elliptical orbits than stuff that is in circular orbits and so on, but this looks a little bit contrived. Now, anyways, the dark matter loss should have happened before very early in the life of the galaxy, before it had time to accrete an envelope. Otherwise, it wouldn't be a relic galaxy, it would just be a regular ETG. The last chairwoman is looking at me. Yeah, I'm running out of time. Last slide. The last possibility, the second possibility we came up with is that this thing lacked dark matter from the very beginning. Think of a formation scenario where you are merging some small galaxies. Those things are gas rich. So the gas stays in the center, dark matter goes through. In order the dark matter not to come back, you require a relative velocity of the order of 2,000 kilometers per second. 2,000 kilometers per second is reasonable for the highest tail of the velocity distribution for galaxies in a cluster of galaxies at redshift 2 or 3. Okay, so this would explain why those things exist, because it's the high tail of the velocity distribution, but why they are rare, because we don't want too many, because we would observe them. So this would be a little bit like a situation like in the bullet clusters, where you have the gas that stays in the center, and whatever stars that had formed and dark matter goes through and doesn't come back. But the analogy cannot be pushed too far, because in the bullet cluster, we have very high temperature gas that has a very low density, so it doesn't cool down. Here we were talking about gas that is orders of magnitude denser, orders of magnitude cooler, so it cools down, forms stars in 1 or 2 dynamical type scales. So I will conclude here by saying that I think that we have sort of proven that for the first time, there's a giant galaxy without much dark matter.